Hi everybody and welcome back. First off, I would like to apologize for the multiple technical mishaps that we had last week. Canvas changed around some of the settings on the instructor side and I thought I knew what I was doing, but apparently I didn't. So that's why you guys all got 20 out of 20 on the problem set last week because, I don't want my technical problems turning into, problems for you. But hopefully this week will be back to business as usual. So here we are in week 11 of the course. This is where I would normally be starting Unit 3 when the course is in a traditional format, so we would have finished up last week, had a test, and then started with the last bit of material here. And so this last part of the class is all going to be focused around what we're going to talk about today, which is hypothesis testing. And so we'll be learning the logic of it and sort of the idea behind it today and going through an example of a relatively simple version of it. And then once we do that, we're just going to be looking at different versions of this same thing that can tell us different things. So the good news is after this week, everything will start looking pretty similar and pretty familiar. So once you get over the hump of learning this, people usually find that the class gets easier as we head towards the end of the semester. So something to look forward to. All right, so I'm going to start out with the general idea of hypothesis testing here. So I want you to just imagine a judge who's up for re-election somewhere that judges are elected and who is making this statement. The average person in New Jersey wants robbery sentences to be 15 years long. If you elect me, I'll make that happen. But from last week, we're going to think about the sample that we used to come up with a confidence interval. And we're going to assume that this is a sample that we have. So we asked 100 people how they would sentence different offenses, including robbery. In our sample, we had a mean sentence of 10.6 years and a sample standard deviation of 5.8 years. So we've got two things going on here. One, we have this judge who's saying the average person in New Jersey wants robbery sentences to be 15 years long. Now we're going to say we have a sample of 100 people that we actually asked about this, and we found that in our sample, the average sentence that people would want for robbery would be 10.6 years. So the question is, based on this sample that we took, how likely is it that the judge's statement is true? And in other words, if the average person in New Jersey really did want a 15-year sentence for robbery, how likely is it that we would have asked 100 people and gotten a sample mean of 10.6 years? And what I've just said here is pretty much what we're going to be doing, except a little bit more formally with hypothesis testing. And the idea of hypothesis testing is that you use a sample to test whether something is likely to be true or not in the population. So in this case, the population would just be, people of New Jersey who have opinions on sentencing. And our sample would be the 100 people that we actually ask their opinions on sentencing about. And we're going to use this sample to try to decide whether the judge's statement is likely to be true in the larger population. And specifically, there are 3 steps to hypothesis testing. And as usual, I'm going to go through these in more vague terms here, especially on this slide, and then I'll talk about each of the different terms on the slides, and then I'll go through examples on the document camera afterwards. So if you still have some question marks after this slide, don't worry, we're going to go through it. All right, so 3 steps to hypothesis testing. The first thing that you're going to do are going to be to write hypotheses about what might be going on. And your null and alternative hypotheses are going to refer to statements about things that might be true in the population. Then you're going to find some sort of test statistic based on your sample that's going to help you evaluate whether or not your hypotheses about the population are true. And then, based on that test statistic, you're going to decide how likely or unlikely it is that you would have gotten your sample values and your test statistic given some hypothesis about the population. All right, so let's now take a more specific look at your null and alternative hypotheses. As I said on the last slide, null and alternative hypotheses are statements about things that might be true in the population. So your null hypothesis is just some statement about something that might be true in the population. In this case, we're interested in whether people in New Jersey would prefer a robbery sentence to be 15 years long. So our null hypothesis, in words, might just be that the mean preferred sentence for robbery in New Jersey is 15 years. So it's some statement about what might be true in the population overall. So we're not talking about any samples, we're really just talking about something that might be true in the population. Another way of writing this would be in the form of an equation. And with the kind of test that we're going to be looking at today, you can write it out either in words like this, so the mean preferred sentence for robbery in New Jersey is 15 years, or you can write it out in the form of an equation where null hypothesis is given by that H sub O thing on the left side of the colon, and then your actual hypothesis is that mu, or the population mean, is equal to 15 years. But these both say the same thing, and they both say that in the population overall, the average sentence that people would want for robbery would be 15 years. Your alternative hypothesis is a statement about what might be true if you were to rule out your null hypothesis. So if you were able to say that your null hypothesis wasn't true, what's the alternative? And that's your alternative hypothesis. So in this case, if we were to say that the null hypothesis isn't true, so we're going to take that null hypothesis that the mean preferred sentence is 15 years. We're going to say that's not true. Well, what's the alternative? And in this case, our alternative hypothesis would be the opposite of that, which is that the mean preferred sentence for robbery in New Jersey is not 15 years. So it's the exact opposite of what we're saying might be true in our null hypothesis. Another way of writing this would be using this notation, so in the form of an equation where you have your alternative hypothesis, or H sub A, and then it would be that mu, the population mean, is not equal to 15. So both of these, again, are sort of broad statements about things that might be true in the population. And your null hypothesis is the one that you end up focusing on in the hypothesis test, and that we're going to be trying to disprove with or we're going to see if we can disprove with our sample. The alternative hypothesis is whatever would be true if you were to disprove your null hypothesis. So we're going to be testing whether the preferred sentence for robbery is reasonably, could be 15 years based on our sample. And if we're able to say that it's not likely to be 15 years, then we'd be finding evidence in support of our alternative hypothesis, which is just the opposite of your null hypothesis. And what we're going to be doing in the hypothesis test then is using data from a sample to decide whether to reject the null hypothesis. So we've got this statement about what might be true, that the preferred sentence for robbery in New Jersey is 15 years, and we're going to look at our sample data and see, based on what we found in our sample, is it likely that that's really the true preferred sentence for robbery in New Jersey? And again, if we do end up rejecting this null hypothesis, so if we say that we have evidence that it's not 15 years, then we'd have evidence in favor of our alternative hypothesis, which is, that it's not 15 years. The second part of that hypothesis test, general format, is finding something called a test statistic. And a test statistic is some standardized value that tells where a sample statistic would fall on a sampling distribution. So that's a lot, so I'm going to go through this piece by piece. So first of all, a sample statistic is any statistic that you can calculate from a sample. In today's lecture and in a lot of what we're going to be doing, we're going to be talking about sample means. But there are other sample statistics that you could calculate as well. So an example of another sample statistic would be a standard deviation. But with the test statistic, we're going to be looking at a sample statistic like the mean. We're going to be standardizing it. So we're going to be converting it from whatever units your sample is in into standardized units. And then we're going to see where it falls on a standardized sampling distribution. So your test statistic is just that standardized value. If this sounds a little bit familiar, it's because you've actually already met things that are used as test statistics. And something that could be used as a test statistic would be a z-score. And another example would be the t-score or t-statistic, which are both the same names, or different names for the same thing. And that's what's equivalent to a z-score when you're working with a t-distribution. So these are things that I drew as part of a different lecture that I then took a picture of and put in here. But what these show are examples of a normal distribution and a t-distribution, and what a test statistic might look like. So if you had a sample mean and you converted it to a z-score, your test statistic would be whatever that z value is. If you're working with a t-distribution, and if you remember, a t-distribution is essentially the same thing as a normal distribution, except that it has different shapes when you have different sample sizes, and it's based on an estimation of the population standard deviation instead of a known population standard deviation. But otherwise, it's interpreted the same way, and it works in the same way. So what you have there on the t-distribution would be different t-statistics that you could calculate for sample means that you might get, the probability of getting each one, that's that bell curve. And then if you were to find the t-statistic for that sample mean that you found, your t-statistic would be your test statistic. So again, to sum up on this slide, your test statistic is just any standardized value that you can calculate for a sample statistic like a mean. So you could calculate a z-score, you could calculate a t-statistic, which is just a z-score for a t-distribution, and then you could see where it fell on that distribution. And by where it fell, I mean where it is along the x-axis. So you can see both of these fall kind of towards the right side tail on these distributions that are drawn. That's where the z-score and the t-statistic would fall along the distribution. All right, so here's the slide I'm re-recording because of, yet again, more technical issues. This is usually the point in the semester where I'm losing battles with the copy machine in person, so, thank you guys for rolling with it. All right, so the p-value refers to the probability of getting a sample statistic as extreme as yours, or more extreme if the null hypothesis is true. And when I say extreme, I mean as far away from the population value that you think might be true, or farther away. So it's either much bigger or much smaller. So that p-value, again, is the probability of getting a sample statistics that's either as big as the one you got or bigger, or as small as the one you got or smaller, comparing it to that population value you think might be true as a benchmark. So that's that, assuming the null hypothesis is true part. The p-value is expressed as a probability, so you'll often see it written as something like p equals 0.02. You've probably seen this in academic papers you've read for classes as well. And what that 0.02 would refer to would be a 2% chance that you would have gotten a sample statistic as extreme or more extreme than the one you got if the null hypothesis is true. So imagine a world where the null hypothesis is true. This is the chance of getting a sample statistic that's as far away from that expected value as the one you actually got. Now in hypothesis testing, we are using the p-value and we're looking at our sample to try to decide if it's too unlikely that the sample came from the null hypothesis for the null hypothesis to be true. So in other words, if our sample's really far away from what we would have expected in a world where the null hypothesis is true, we say that the sample gives us evidence against the null hypothesis. It's evidence that the null hypothesis is not true. But then that raises the question of how unlikely does your sample statistic have to be in order to rule out the null hypothesis as being true? And we define that level of how unlikely it has to be using something called the alpha level. And specifically, the alpha level is just a threshold that you choose before you run a hypothesis test that tells you when to reject the null hypothesis. So as an example alpha level, you might decide to reject the null hypothesis if there's only less than a 5% chance that you'd get your sample statistic from a population where the null hypothesis were true. And common alpha levels used in social science research are 0.05, 0.01, and 0.001. 0.05 is the most common. It's sort of considered like a universal standard in a lot of social science research, but you will see the others pop up as well. And so an alpha level of 0.05 would be interpreted like that first statement there, which is that you would reject the null hypothesis if there's less than a 5% chance you would have gotten your sample value from a population where the null hypothesis were true. The other ones would have the same interpretation, so an alpha level of 0.001, for instance, would mean that you would reject the null hypothesis if there's a 0.1% chance that you would have gotten your sample from a population where the null hypothesis were true. So why pick, different alpha levels? Well, there's trade-offs to alpha levels that are larger or versus smaller. If you have a larger alpha level, like 0.05, it's relatively easy to reject your null hypothesis because you have, 5%, you're rejecting your null hypothesis if your sample falls in the 5% of least likely possible values that you could get. So even if the null hypothesis were true, 5% of the time your sample is just going to be in one of those really far away spots anyway, and you're going to reject it. So you end up with more false positives that way, and that means that you really have weaker evidence about what's going on with your null hypothesis. So it's easier to get a reject, which is like a false positive, which is like a sort of a positive, yes, we reject it, but it's more likely that you're going to reject the hypothesis just by chance, even if it actually is true. If you have a smaller alpha level, so an alpha level like 0.001, it's harder to reject the null hypothesis because you're only using samples that are really, really, really unlikely to rule out the null hypothesis being true. This means that when you do reject the null hypothesis, you have stronger evidence that the null hypothesis is not true. But the downside to this is that sometimes you're going to fail to reject the null hypothesis when it really is true. So you might get a sample statistic that's pretty far away from the value specified by the null hypothesis. But if it's not in that 0.1% of least likely possible sample statistics, you're still not going to be rejecting that null hypothesis. But the key takeaway here is that the alpha level is chosen by the researcher, by the person who's running the hypothesis test. In this class, it will be chosen by me generally, to reflect whatever the purposes of the research are. So you're not calculating anything here, it's just chosen as a threshold where you decide that you would reject the null hypothesis if your sample falls into a particular zone on the graph. And we're going to look at what the graph looks like in a little bit. As a general rule, though, when thinking about these numbers, your p-value and your alpha level, you reject the null hypothesis if your p-value is less than your alpha value, and you fail to reject the null hypothesis if your p-value is greater than your alpha level. So if the null hypothesis, if your p-value is less than your alpha level, it means that your sample falls into that zone of samples, possible samples that you could get that's really, really unlikely if your null hypothesis is true. Because the probability of getting your sample statistic, or one as extreme as yours or more extreme, is less than that probability that you've roped off as being too unlikely to come from a world where your null hypothesis is true. On the other hand, if your p-value is greater than your alpha level, it means that the sample statistic you got is one that would be pretty likely to get if the null hypothesis were true, where pretty likely, again, is just defined by whatever cutoff you've chosen for your alpha level. A quick note here, and I think I also say this in other parts of the presentation, but now that I'm recording this like 3 days later, I'm going to say it again. You always either say that you reject the null hypothesis or you fail to reject the null hypothesis. And you never say that you accept the null hypothesis, or you also never say that you accept the alternative hypothesis. The reason for this is that with our sample, we can either get evidence that tells us that the null hypothesis is probably not true. So that's if your sample value is really far away from what you would have expected if the null hypothesis were true. So that would be evidence that would let you reject it. Or you can find that your sample would be, pretty likely to get if your null hypothesis were true, in which case you'd fail to reject it. But no sample can actually tell you exactly what the population value is, because there's always sampling error. You never know exactly what that population value is and where on the sampling distribution your particular sample falls. So we can never prove that the null hypothesis is true. We never accept it. We can only fail to find evidence against it. And same with the alternative hypothesis. We can reject the null hypothesis, which would lead us to think that the alternative is probably true, but we can never actually prove that whatever value is specified by the alternative hypothesis is the right one. All right, so I somehow managed to record over what was on this slide too, so I'm just gonna go through this one again. Take 2 here. So The hypothesis test that we're going to meet in this lecture is one that lets you answer the question right here, which is that we're going to be able to ask whether the true population mean is likely to be equal to some value that we specify. And as we go through the semester, we're going to meet other hypothesis tests that let us answer other questions, but this one is the most straightforward, so it's the one we start with. And to answer this question, we're going to go through 3 steps that follow the format that I outlined earlier in the lecture. So it's called a one-sample t-test when you're asking if the true population mean is equal to this. The t-test part refers to the t-distribution, which we'll be using to run this particular test. And these are the steps that you would follow. So the first thing you do is write out null and alternative hypotheses. So that's step 1 in any hypothesis test. So we're writing out something that might be true about the population, and then whatever the alternative of that would be, that would be likely to be the case if you rejected the null hypothesis. For our next step, where we find a test statistic, we're going to be finding a t-statistic for our sample mean. So we're going to be using the t-distribution, which is a sampling distribution for means, in which you don't know the standard deviation of the variable in the population, so we're estimating it. That, if you remember from last week, means that you have a slightly different shape for some different sample sizes because it's accounting for that extra uncertainty. Otherwise, though, it functions like a normal distribution, and t-statistics or t-scores, I warned you I'm going to sort of use those interchangeably here, but they are equivalent to z-scores on a normal distribution. So just like you could have a sample mean value and find a z-score for it in a normal distribution, you can have a sample mean value and find a t-statistic for it in a t-distribution. And then you can figure out, where in your sampling distribution that falls. Is it sort of towards the middle? Is it out in the tail? We're going to be looking at that. The next thing we're going to be doing is using that t-distribution to decide whether to reject the null hypothesis. And specifically, we're going to use the t-distribution to find a p-value that tells us how likely our sample mean is in a world where the null hypothesis is true. And if that p-value is smaller than our alpha level, we're going to reject the null hypothesis. So with this, I'm now going to take you guys over to the document camera, run through examples of a one-sample t-test. The first example, as I usually do, is going to involve a lot of steps along the way where I describe what I'm doing and why I'm doing it. I'm also going to bring in the sampling distribution and connect this material to what we've been doing over the last couple of weeks and kind of show you where some of these things come from. And the second example will be much quicker, where I just run through these steps without all the explanation. So here we go.